Good afternoon. Thank you for being back. So we now have two sessions back to back. The first one will be more focused on architectures. So how to use all those building blocks that we saw before to build architectures that can solve common use cases. And the second one will be focused on availability and global deployments of serverless architectures across the world. So something that in the past was probably in the hands of a very few very large companies. Now anybody can do global deployments with serverless without incurring huge costs. So it's quite an interesting use case. So let's start with the architectures. So today we will see and review together a few standard architectures that we've seen our customers are using a lot, especially web applications. We will focus on things like how to manage authentication, data lake. This is a key trend in all enterprise data processing, stream processing, how to manage data in almost real time. We will focus a little bit also on operations automation, so how to automate those IT scripts that normally we run, but maybe not in a reliable environment like Lambda can be. And the final one is different. It's not something that we've seen with our customers. It's more a new key trend where we're launching new products now. We've seen lots of interest in GraphQL to provide a different way to build web APIs. And GraphQL allows you to build real-time backends that can also help you work offline. So if your client is not connected, you can still work and then resynchronize. So I will give you a little bit some details on this new key trend. So that's more an advanced topic, but I think it's interesting to understand where we are going in that area. Before starting, just a recap of few best practices that I think it's important. So to reduce the cold start, so the time it takes to invoke Lambda when we first have to create a container, or when we scale and we have to create an additional container, try to think to minimize the package size, the dependencies. And this is especially true for people coming from enterprise development backgrounds like Java or C#, where you usually add 10 megabytes just for logging with libraries. Now it's better to have a different approach. Also, JavaScript is quite affected. You saw when I installed with NPM one dependency, you bring half of the web with you inside the node modules. Also, from a security perspective, I think minimizing dependencies is not a bad approach. One tip that I didn't give, but it's really interesting, separate the logic of your application from the Lambda handler. So you saw there was this function that was processing the event. Especially if you want to test locally, or if you want to give different interfaces that are not Lambda to the logic of your application. Use maybe the Lambda handler more as a wrapper that takes the event and set it into your internal data format, and then call another function that is the main entry point of your business logic. It's better, so you separate your custom implementation from the Lambda integration. Use environmental variables for having the same function across different environments, and encrypt using KMS the secrets that you put into those environmental variables so that they are decrypted only inside the memory of the environment where the function is executed. Again, manage the dependencies of the function carefully. And we saw how the memory gives you more CPU power, but memory brings also normally more cost unless your your application is really CPU bound. We have a metric that you can see from CloudWatch that tells you how much max memory was used by your function. You can also see that in the console. So use that as a tip to understand how much memory you really need, because otherwise you really don't have a starting point. And every customer has 75 gigabytes of space in every region for all your Lambda code. Normally, that's more than enough. But especially if you start to keep in multiple versions, or you have tools that automatically store new version every time you update a function, you can run out of that space. And this is a hard limit, so we don't increase that. So there are lots of scripts now that have been created by people that can help you like delete the older versions of the functions you have. But keep this in your mind, because if you discover it the day you're going in production, it may be slowing down your development. So let's start with the first pattern. So web application or any microservice with API with a web front end. So this is the standard architecture of a serverless web application. On the top, we have the static content, like the HTML, the media content, images, style sheet, the JavaScript code that is run on the browser or on the client. And normally, this is stored on Amazon S3, our object storage. And you can use CloudFront, our content delivery network, to further enhance the speed and reduce the latency when you download the static content. And below, we have the dynamics part of your website. So the APIs, for example, that your single-page application is calling. And this can be implemented, as we saw, using the Amazon API Gateway that is running one or more Lambda functions in the backend. And this Lambda function can do anything. Normally, you will need to persist information somewhere, because Lambda function, they don't store data by themselves. So normally you use a database. Most of the time, and DynamoDB can be a good choice because it's, again, serverless by itself. But you can use any database, or you can use another S3 bucket for storing the information and the data of your customers if there's unstructured data that doesn't fit a normal database. To manage the authentication and authorization of the users, there's multiple ways to do that. What I suggest is have a look at Amazon Cognito, especially Cognito user pools. It's the easiest way that we developed over the year. And it's very well integrated now with other technologies. So this is an architecture that is really popular. We have lots of customers. Just to give you an example, this is Bustle. It's an entertainment and lifestyle website targeting women with this content. And they basically reduce their costs by 84% when they switched from the traditional architecture to a serverless approach with a similar architecture to what we saw. And now they feel that their engineers are really focused on building innovation, on keeping the things and the lights on in their infrastructure. So how can we secure this architecture? So starting from the top, on S3 buckets, you can create bucket policies that are policies similar to the policies that you give to a Lambda function, where you can define who can have access to this, the content of these buckets. It can be very granular, so you can say this prefix is public, this other prefix is like the directory, is private, and so on. You can also define object-level access control list, so a single object can be public, private, or can give given access to a subset of other users. Be careful, because it's easy to make mistakes. That's why we have lots of tools like Macy that can help you monitor if you make a bucket public. And also, if you have something in your bucket that is public, we now integrated that also in the console. So now the console visually tells you if this bucket has some public content or not. If you need to have public information and private information, since buckets, they don't cost, you pay only for the storage, my suggestion is use two buckets, one that has private content and one public, so that you avoid any possible human error in giving permissions. You can avoid giving access from outside to Amazon S3 completely, because you can use origin access identity. It's a way to link a CloudFront distribution with an S3 bucket. In this way, only CloudFront, the content delivery network, can read from or write from, in this case, normally read from Amazon S3. So that's a very good way. It's integrated in the console. And so in this way, you can have a private S3 bucket that contains maybe the static component of your web application. And then CloudFront is doing the public distribution of the content. CloudFront has lots of fine-grained control that you can add. So it implements geo-restriction. Geo-restriction, luckily the screen continued to work. I don't know if someone shut the lights. Yeah, OK, thanks. So geo-restriction is normally used more for licensing. Most of the time, when you use a CDN, you want to distribute content that has some sort of licensing, like media content. So with geo-restriction, you can say this content can be seen only in these countries, and we will check that the IP address is coming from one of those countries. It's a feature. Then you can sign content, so you can give access to content only if it's signed with cookies or with specific URL that contain a signature. So you can have private content that is shared only under those circumstances. And you can manage the signature, for example, with the API gateway that can generate the signature and give it back. to the application, so that then you have a signed link that gives you access to private content. And as I already said before, it also will transparently manage DDoS protection. So you don't have any network connection with CloudFront. It will be your front end, and it can absorb or block DDoS attacks in multiple ways. On the dynamic side, usually you protect your database if you use DynamoDB and your Lambda function using identity and access management roles, as we saw today. So you have a role that tells what the Lambda function can do, and a role that tells who can call the Lambda function. So 2 different roles. And the Amazon API Gateway is quite integrated for security. We will see for authentication, but generally it can check throttling, caching of content. It implements usage plans so that you can give different usage plans to different tiers of customers that have different throttling. And it's also integrated with the Amazon Certificate Manager. So you can deploy your own certificate for HTTPS so that you can use custom domains instead of those ugly, randomly generated domains. You can use Let's Encrypt if you want. But it's completely integrated out of the box with our certificate manager, and we generate certificates for free. So you don't pay anything, and we also manage automatically the renewal of certificates, so that even if you forget, we will automatically and transparently renew the HTTPS, the SSL certificate for you. So there's no cost, and now you can, the first version of ACM, you should like validate via email the new certificate. Now you can use the classical DNS validation of new certificates. So it can be automated even if you have lots of domains to manage. You don't need to have emails for the automatic renewal of the certificates. For authentication and authorization, you can use Cognito that can enter into the identity of the users and give access to all or part of the APIs of the Amazon API Gateway. So there are different ways to do that. So you can use IAM, but the way I would suggest is to use a custom authorizers. And there are 2 ways to use a custom authorizer. One is the Cognito user pool that we will see later, and one is to use the Lambda function. So the Lambda function is a nice trick. Basically, what you're saying to the API Gateway is, I create a custom Lambda function that you can write with whatever code you want, and this Lambda function will check the authentication against any possible authentication service that you want to use, because you can manage the integration. And the custom authorizer can work in 2 ways, either with a token. So token means that there is a token that is passed in the header, and this token is what the Lambda function receives. And you can use only the information in this token to decide if this user is authenticated and who is this user. Or we more recently added the full request access. So now the Lambda function can have access to all the payload of the HTTP request and understand who is this user and if he has access or not to my resources. So this is something that is custom built by you, but it's completely flexible. And the Lambda function is not invoked for every interaction. So you can define like a time limit. So if I authenticate a user, you can say for some minutes or hours, it's still authenticated with the permission that I give. And then and with the custom authorizer, you can also set context-specific information that will be passed to the Lambda function. So basically, you can set information like the role or the security level of the person, and this information will be passed to the Lambda function so that you have more context information on who is the person accessing this API. The custom authorizer is also integrated with Cognito user pool. Some time ago, it was basically, we were automatically generating the Lambda function for you, but now it's completely transparent. So if you enable, you just can use Cognito user pool with users. It's a user directory that we manage for you, including the login password page. So basically, you have a link where you can go and do the web authentication. You can customize the login page if you want. So it's completely transparent. This is an overview of all the possible options. So basically, Cognito identity pool, that it's the first features that we launched with Cognito a few years ago, usually works trusting a web identity provider, such as Facebook, Twitter, Amazon users, OpenID Connect, such as Salesforce, for example, Google accounts. So you can basically, in this way, you do the authentication using the SDK on the third party, like Facebook or Twitter. And then you use the token that they give to you. You give the token to Cognito. If Cognito is configured to trust that identity, it will trust, and you have Facebook authentication very easy to implement. Or you can create your own user directory with Cognito user pool. And this user directory can work together with web identity. So basically, you can have users from Facebook or users with your own users together, or can go the direct route using the custom authorizer with the API gateway. I know there are different options, but authentication is something where every customer wants to do things differently, so we implemented lots of possibilities. The default, if you start from scratch, use Cognito user pool and go straight to the API gateway with the custom authorizer for the user pool. And this is just a summary. So in this way, you can really fine-tune. So the web identity provider gives access to a role. So for example, the user here can have access only to a specific API. If it comes from Cognito user pool, you can give access to other API. And a different one is it comes from directly from the user pool. Now, as I mentioned before, the API gateway that was only edge optimized. So before this release, a few months ago, all APIs were automatically distributed to CloudFront through our content delivery network. Now you can create regional level APIs that run inside an AWS region. And among other things, this allows you to do interesting things with the DNS. Because if you want to control, we will use this when we will build in the next session the globally distributed application. Your API has an HTTPS domain. And this HTTPS domain must match the domain that people is using through the DNS and the certificate that is inside the API gateway. So if you want everything to work correctly with your API and don't get those errors with the security on the browser, with regional level, you can deploy the same certificate in multiple regions and then do load balancing, for example, from outside. These kind of things were simply not possible before because the certificate was at content delivery in the content delivery distribution network, so outside of the region, and basically you couldn't control direct access to, for example, my API in Europe versus my API in the US. There's quite a few frameworks that can help you if you want to start from scratch. Those are the frameworks open source that we support as AWS because we develop. There's tons that are not here, like the serverless framework, for example. So Chalice is very good if you come from, if you develop in Python with tools like Flask or Bottle. So you basically have the same syntax. And there's also a couple of open source projects that do similar things and that are very good, Zappa and Claudia.js. Last time I was in a conference, a guy was doing his wedding, and he built his wedding website using Django that runs on Python. And since if you're not very popular, your wedding website doesn't really get so many hits, he just used Zappa to wrap everything, and he deployed using a Lambda function, and with zero cost, because it was in the free tier, he managed this wedding website. So nice story. The Serverless Express framework helps you take a Node.js Express application and wrap it inside a Lambda function. So with almost no change in your code, almost, because you can fine-tune something if you want to get the context from the API gateway, but normally you don't need it. You can really take an Express application, wrap it, and have it all running inside a single Lambda function. So it's not very granular, but it works. And similarly, we have for Java. So if you have servlets or Spring application in Java, we can wrap them and have them run inside a Lambda function with these tools. Second pattern, the data lake. So this is something where we've seen lots of interest. So in the past, building data analytics for companies, especially for enterprises, was basically using an enterprise data warehouse where you collect your data, you aggregate, and you store in an analytical large database that has a sort of relational interface, but normally internally works differently from traditional relational databases. Now we've seen there's lots of interest in keeping more data, simply because storage costs are very low. Think of S3 with the life cycle. You can store anything, all the logs of your application, all the phone calls that your support receives, all the picture that you take maybe inside your shop to understand if people is smiling or crying in a specific site of your retail space. So you can keep this information. It's not normal data anymore. So the idea is that you want a place where you can store any kind of data, structured data and completely unstructured data like images. You want to be able to run classical BI or even advanced AI machine learning algorithms on top of this data. You want to have a very fast ingestion because here you have big volumes. You want to have something like schema on read. So since you are very flexible in the data that is put here, you want to have some features like if I want to read the data, there should be some API that gives me the schema of this data dynamically so that I don't have to put the schema inside my application. I can create something that discovers the kind of data. This is a picture. This is a record with this structure. It's JSON. It's CSV. This is normally complementary to the traditional enterprise data warehouse that we've seen built over the years with company. And another approach at architectural level, since you have lots of data and sometimes you run lots of computation, but then sometimes you just keep the data, you want to decouple compute and storage in this architecture. You want to store lots of data, and then sometimes you want to run some analytics, and then you need tons of computing for a few hours or a few days, and then you release this computing. So those two components should be decoupled. So we see as the main building block for this kind of architecture Amazon S3, the object storage. You can use lots of different tools, but specifically the Kinesis platform to manage the ingestion, so to collect data and store data here. So we have streams, firehose. More recently, we also launched Kinesis Video that can help stream video data, not to S3, but to be processed in that case. You can build a catalog using building blocks like DynamoDB and Elasticsearch. The Amazon Elasticsearch service can be the two main building blocks where DynamoDB stores the information and Elasticsearch provides you the possibility to search for content that you stored. And Glue, AWS Glue is a service that does lots of things. It can how to discover the data formats you're using and can run data pipelines, so that takes data from some sources, process this data, and then stores the data in other components. For analytics and processing, you can use, of course, Lambda on top of S3. When you store something on S3, you can trigger a Lambda function that can be doing the processing or can start a processing of the data. We have Amazon Athena that you can use to run SQL query on S3 straight without having any database. So we support a few formats, and you can just run your queries. QuickSight is a business intelligence visualization tool that runs normally on top of Athena or on top of most of the relational databases. Glue already, as I said, can also process the data. And Redshift and Redshift Spectrum are our own analytical databases that you can use to run queries. So Redshift Spectrum allows you to keep data inside Redshift, that is a columnar analytical database, and also run queries with data that is on S3. So you can join data that is inside Redshift, the database, with data that is kept on S3 in the same query. For security and auditing, of course, you can protect everything with the usual permission, so IAM. You can encrypt anything on S3 with the key management service. And you can also audit who is accessing data, also who is reading the data using CloudTrail. Usually, this is very important for compliance, knowing who has access to your data. And we also have a service that is called Amazon Messi. This is a machine learning service that will automatically analyze your data on S3 and classify the data to see if there's some personal identification data, so that it will automatically tell you the kind and the security of the data that you have on S3. And it can also check other access to your account. For example, when I enabled it, I was on holidays in Italy. I created an account, and account created from a country different from your usual country. It just popped up in the console. So Amazon Messi can really check your data and the activities on your data to see if there's something different than usual that pops out. For building an interface to a data lake, so normally the user of a data lake are not technical users. You need to provide an interface. You can very easily build something with the API gateway and Lambda, a traditional web application that can help you understand and use the data in your data lake. So S3 is the foundation for multiple reasons. So with S3, you can store data without any limits. I think, do you know, who has never used S3 here? So very little people. So it's very flexible. You don't have limits in the number of objects you store, the size of the object, each object up to 5 terabytes. The bandwidth scales with the data. So the more data you have, the more bandwidth you have to analyze the data. We also implemented different storage classes, and we can automatically move data across different storage classes to make it cheaper for you. We implement versioning, so you can store multiple versions of a single object, and transparent encryption if you want. New features that we launched are CloudTrail data events. So if you have sensitive data, you can have an auditing log that tells you who has access and when to the data you have in specific S3 buckets. This is very important for compliance. We have 2 features that we launched last year, but were not so famous, I think, but very useful. S3 Analytics will automatically assess how you use the data on your S3 buckets and tell you if you should change your storage class to reduce your cost. So maybe you take something online, but you actually don't use it so much. AWS config can also implement automated checks. For example, if someone is changing the permission of an S3 bucket to give public access, AWS config can enforce a rule that will block this and notify the administrator that someone was trying to make public a private bucket. You can tag objects, any file on S3, so adding metadata for a data lake usually is good. And more recently, for S3 and Glacier, that's our cold storage, we launched a feature that is called Select. So that means that the storage can natively run select queries on the data. And this scales with S3. So if you run a select on S3, it will be automatically distributed to all the compute nodes that S3 use. So you can really do interesting things here. This is a standard architectural pattern that we've seen a lot for analytics. And it's using DynamoDB and Elasticsearch together. So DynamoDB gives you very high throughput query possibility. So if you index data, you can retrieve information by key very quickly. It has some indexing, but it's not a search database. So the idea here is that when you store data on S3, you can you trigger a Lambda function that will index the most important metadata by key on DynamoDB. And this can also trigger another Lambda function straight from S3 or from the update to DynamoDB that will take this metadata information and store it on Elasticsearch so that now you can search for this data in any way you want. And this Lambda function will keep every metadata that is stored on DynamoDB searchable on Elasticsearch. So you synchronize the 2 repositories, and you can use both. So if you have high throughput data processing that needs to collect information by keyword, you go on DynamoDB. If you need to search all the files that mention a certain keyword, you can search that on Elasticsearch and then get more information going back to DynamoDB. So it's quite a pattern that we see having these 2 things synchronized. And we have our default Lambda function to do that. So you don't need to write this Lambda function. You can find it in the console. I think we set it up automatically if you want. This is another example of how you can use AWS Glue. So AWS Glue is another service. We launched it last year, not this reinvent, the previous one. And it does multiple things. One thing that it does is it has crawlers that can automatically look for the data you have on S3 and then understand what kind of data and the structure of the data and create a data catalog that is compatible with Hive, the open source project. And this is the same standard that is used by Athena and Redshift Spectrum. That means that you put the data there. It can be in CSV, Parquet file, lots of different formats. And this will be automatically discoverable by Athena or Redshift Spectrum to run queries on top. So if you want to run queries only on the data on S3, you can use Athena. If you want to do a join between what's inside Redshift with data on S3, you can use Redshift Spectrum. And in both cases, you can use QuickSight to have a graphical user interface that can help you navigate the data and understand what's happening. For analytic and processing, you can use, again, the tools that we saw. I just want to add to the loop Amazon Elastic MapReduce, EMR. So lots of people use Spark or Hadoop, and those tools are fully managed within EMR. So they usually are very well integrated with Kinesis or S3 for data processing. This is an example of how you can run Athena on S3. So in this case, we run this query. It's on a standard database of n-grams, so of how you use words in documents. And it's processing 170 gigabytes of data. You get the results in 44, 45 seconds. And since with Athena, you pay only for the data you process, in this case, you pay 85 cents for this query that is processing all this information. Athena, actually, as I said, you pay by the data you process when you run a query. So instead of giving raw data, you can optimize the data. So if you use partitioning, so if you store data on S3 with this format, so you use folders where you have variable type equal value. So you can have, for example, years, months, and days if you store by date. You can have any keywords depending on your data. This will be automatically used by Athena in the queries. So instead of processing 170 gigabytes, you only process the folders where the data is. So if you put a where clause where the month is January, only the folders with month January will be processed. You can also use more optimized formats for Athena. It's columnar formats. So that means that the data is stored so that you can only read the single columns of the data instead of all the records. Most of the analytical queries, you only process a subset of the columns. So you can have records with lots of columns, but you need to filter and extract only a few of those. So if you use Apache Parquet format, Avro, or Orc, you get this benefit automatically. So maybe you already have software that can import or export those formats. If you don't use Parquet or Orc, you can still compress the data. If it's compressed, you pay for the compressed sites. So it's cheaper and faster. But you need to use splittable compression platform like BitZip2. So gzip doesn't work. BitZip2 and other tools allows you to read and split the file in a better way. And you have this blog post where we show how the same files, depending on how you store them in different format, gets different performance and different cost for the same query. So you can really optimize your cost and your speed a lot, looking at how you store your data with Athena. How can you process batch data? If you want to use Lambda, we already said Lambda has a timeout of 5 minutes. So maybe you can't process the data that you put on an S3 bucket in 1 minute. Because maybe it's a large file. So the architectural pattern that we saw lots of customers implement is the splitter. So you can have a first function that is triggered by S3, looks at a very big file, and then splits the data and launch technically up to 1,000 functions in parallel to process the data. And you don't need to actually split the data because S3 has the range operation. So with S3, you can read only a subset of a range of a file. So for example, if you upload 1 terabyte of data and this triggers a Lambda function, the Lambda function can see the size of the file and then launch multiple Lambda functions. Each function has a different range of bytes inside the file that will be extracted and read by each function so that each function can process the data within 5 minutes and usually store the information in a central place where you can have a reducer that will collect all the information back and provide a single result. If you look at this architecture, is a serverless implementation of the MapReduce architecture that was popularized lots of years ago by Hadoop and Google before of that. And this is architectures that are used actually in production a lot. So this is Fannie Mae that I didn't know, but I discovered it's the Federal National Mortgage Association in the US. So they basically do lots of analytics to support the mortgage market in the US. And they run Monte Carlo simulation. Monte Carlo simulation means that they use random simulation to understand the possible path of what can happen depending on the stock market and everything in the financial market that can affect mortgages. And they run like simulation of 20 million of mortgage Now it takes 1.4 hours using this approach of serverless and parallel Lambda function that is 4 times faster than it was before when they were using a traditional architecture. And it's much, much easier to manage because now they can scale from 1 to 1,000 Lambda function just with a trigger. If you use Python, there's this nice library. It's called PyVran. And basically, the idea of this Python library is to provide you a framework where you can take your computing logic in Python and run it in parallel on lots of Lambda functions. And they achieved peak performance now with the limit of 1,000 concurrent functions that we are happy to increase, but it's there. You can get up to 10 teraflops of computing power. It's a lot. And they can read, for example, at speed like 60 or 50 gigabytes per second, read and write from S3. So throughputs that normally requires lots of optimization, this comes out of the box if you use their library. Third pattern, stream processing. So this is different. So now we want to process data almost in real time. The definition of stream processing is not very close, so there's different interpretation. For me, we're talking about stream processing if you have a high ingest rate, and high is relative but means something that you can manage with traditional architectures. You have the purpose of your architecture is to process this data with low latency. So from data injection to getting the result of your process, this time should be as little as possible. Probably in the matter of seconds or minutes. If it's hours of days, this is not streaming. You can have spiky traffic. So you don't normally streaming applications are sensitive to the source of the stream. Sometimes the source of the stream can be IoT architecture or business application. Either way, you will have peaks that then go down, so the traffic is not steady. And they usually need 2 main characteristics. So that message durability means that you don't lose any of the data that you receive. Even if you have high volumes, you still need to process exactly all the data that is sent. And message ordering is important. So you can't process the data in a different order than the order you receive. And for people that studied a little bit of distributed systems, they know that durability, ordering, and distributed systems are 3 things that normally don't work very well together. You need to put some sense to do that. So we, over the year, created the Kinesis platform that can help you manage this. And it's still serverless because you don't need to manage any server, and it's fully managed. So normally, you can have an architecture like this. And for data injection, we have a specific service within Kinesis that is Kinesis Firehose that can help you store the data almost without writing any line of code. So you just need to put the record into a Kinesis Firehose delivery stream. You can use our SDK to do that. We also have some agents that you can install if you need to do that from, for example, physical devices that have some limitations. And when you receive these records can automatically be buffered and written to S3. So buffered means that if you receive 1 million of records and each record is 100 bytes, you don't want to write 100 bytes files on S3 because then it would be crazy to read and process this data. But you can set up some buffering rules so that this data is aggregated in files and much more manageable on S3. We can also automatically load the data on Redshift, our database, so that you can then run SQL queries. Or store the data on Elasticsearch, where then you can run all the Elasticsearch queries. Sometimes you want to pre-process the information. So we have the possibility to insert a Lambda function that is used processing each record. Not each, the invocation is not for each record, but we process it in a micro batch. So every 100 record, 1,000 record, you invoke this Lambda function. It's automatic. And this can do some processing or enrichment of the data. So you can check the syntax. You can add more information. You can even do lookups on external database to enrich the information from your customer database or your IoT device repository. And then you have the transform records. If you use this function and you transform the input data, it's good practice to enable the source record backup. And basically, we will store also a backup of the original records that you receive, so that if something goes wrong with your Lambda function, you still have the source data that you received, and you can reprocess it. And everything is stored as a metric on CloudWatch. So on CloudWatch, you can check the volumes of the data, and you can check if you're keeping up with this data processing or not, because maybe your function is too slow and you're not able to keep up. And then there are a different approach to solve this kind of problem. So as I said, with Firehose, you can call Lambda functions with a buffer size. So normally, the default is 100. That means that every 100 record you receive, you invoke the Lambda function. It receives this, in the event, a list of 100 records. And then you can process the records and send the output. Normally, playing with these characteristics can help you scale the function better. When you store the information on S3, you have two other parameters that you can use. And it's the buffer size and the buffer interval. So basically, you can tell to Firehose, you're receiving lots of small records. Every time you reach, I don't know, 100 megabyte or a size that you specify, or 15 minutes or 1 hour has passed, so the first you reach, you store a file with all those records on S3. So in this way, you can buffer and group the data in a much more manageable way on S3. And you can also transparently enable compression, so that the data can be stored compressed for you on S3. If you store data straight to Redshift, it's a database, so you have to be a little bit more careful. So there's this link that you will get with the slides, tells you more information. There's a blog article that gives you more information how you can optimize data to be stored on Redshift, especially if you do time series or things like that, or data is sorted. You can have some tricks so that data is processed in the most efficient way. This is an example of an architecture that is quite common. So you have IoT devices, and you want to process the information from these IoT devices in near real time. So in this case, we have lots of IoT sensors. They use AWS IoT, so they can communicate using a machine-to-machine protocol, like MQTT, or we're now opening AWS IoT to lower-level protocols so that are usable by devices that don't even can do TLS on TCP, so very low-level devices. So these sensors can send information to the AWS IoT platform. And there you can set up rules that, depending on the content of the record, can send this data for injection or processing to the AWS cloud. And you can either just store the raw records, but in this case, every record becomes an object on S3. So if you have very small records, it's not efficient. You can send this to a Kinesis data stream, and here you can process the data with a Lambda function. Or you can send the data to a Kinesis Firehose delivery stream that stores the information on S3. And a trick is using buffering, you can create a file, for example, every 5 minutes or 15 minutes. And this can trigger a Lambda function that can process the whole file together. So it can be a good way if you don't need to be very low latency to optimize your cost. This is how you can do real-time analytics. So from the producers, you get the Kinesis stream that is ingested from the IoT devices or whoever is producing the data. And sometimes you want to look, for example, to some variables that need to be smoothed over time. So let's say that you have sensors that gives you the temperature of lots of different places in your factories across all over the world. And if one of these rooms reach more than 40 degrees, I want to act and do something because it's too much. But you can't trust a single data point. So you can use Kinesis analytics that can run and create a tumbling or a sliding window on the data and create an average across a period of time. So you can say take an average every minute, and that's a tumbling window. Or you can say for every data point, take also the average across the last minute of data. So that's a sliding window, because for every data point, you scroll the slide and the window to get smoother data. Kinesis Analytics can also do anomaly detection using the random cut forest algorithm. So that means that based on all the data that you receive, it can statistically infer if this data point is probable or not. So basically, you add a probability to every record that tells you this is a record that is 95% correct, or this record is probably coming from a sensor that is sending wrong data because there were so many few records with this kind of information. Maybe it's broken. And the output of the Kinesis Analytics platform that can be aggregated, so maybe here you receive millions of records, but then you aggregate every minute. This Kinesis stream can then send the information to a Lambda function that can check the average temperature every minute from your millions of sensors and act only if effectively the record was sent with multiple data points saying that this room has this problem and maybe there were no anomalies in the device. And then you can act and maybe send an SNS notification to a support team that can go there to recover the issue. Kinesis Analytics will automatically infer and inspect the structure of the data that you send. It can support JSON or CSV formats, for example. But sometimes a few records may not respect this data format. So you can automatically configure an error stream where any record that you receive that syntactically is not correct is sent so that you can have your error records to be processed maybe through a different platform. Let's see how this Windows aggregation works. So with Kinesis Analytics, you can use a syntax that is similar to normal SQL to aggregate data. So we're running now SQL not on a table, but on a continuous stream of data. So to do that, we use the blue part to define the input and the output stream. Then we have the orange part that defines the tumbling window. So basically, we're saying that we are using the raw time, so the time where this record was injected in the platform, and we aggregate by 1 minute, but you can use any syntax you want. You can use seconds, hours, if you prefer. And then on this data that is aggregated, we can run the sum of a specific measurement, so maybe the sum of the temperature, and we also count the samples. And when you have the sum and the number of samples, it's very easy to build the average as a consequence. So this is an example of the syntax. So apart from these blue parts that are a little bit specific to the input and output stream, the rest is mostly plain SQL. And then there's this syntax to create tumbling, or if you prefer, sliding window. The difference is that tumbling window will reduce the amount of data because data is aggregated. So if you have lots of records, you aggregate every minute, depending on the keys. A sliding window will output the same amount of records that you receive, but will give you the average of a specific value over time. So usually they smooth specific reads that you can receive from devices. And this is the architecture that we saw. Let's see a little bit here the Kinesis stream part. So this is the third type of way you can invoke a Lambda function. You remember we said that when you call a Lambda function, you can call it synchronously or asynchronously. This is the third way that is designed to preserve order in records. So what happens is that when you create a Kinesis stream, you can scale adding multiple shards. Each shard has a throughput of an input ingestion throughput of 1 megabyte per second. So if you need to receive more than 1 megabyte per second, with Kinesis, you create multiple shards inside the same stream. It's just a configuration. You can even auto-scale it using Lambda functions if you want. What we will do, we will create a Lambda function listening to each of your shards. So if you have 3 shards, we will have 3 Lambda functions listening. In this way, each Lambda function receives data only from a shard and can preserve the order inside the shard of the record that you receive from sensors or databases or whatever. So this means that you have basically 2 ways to increase performance. One is to increase the batch size, so how much records at a time you want Kinesis to send to its Lambda function, so each shard to its own Lambda function. The second one is that you may need to increase the number of shards even if you don't need too much injection power because you need more Lambda functions to process the data. What we've seen also used by customers is the fan-out pattern. So the fan-out pattern is similar to the S3 pattern that we saw before. You have a first Lambda function that is not doing all the work, but it's just taking the raw data and then starting in parallel multiple Lambda functions to process the information. This works, but you lose the order because each of these Lambda functions is invoked asynchronously, so you lose the order. So it can work for some use cases. For example, this is the architecture that is used by Thomson Reuters. They have this product insight where they collect all the information from how their users are using their platform. So all their business software is sending information using Kinesis. They normally have 4,000 requests per second, but they reached 10,000 data points per second with this platform. And they have the data from when it enters in Kinesis and it's in their user dashboard in less than 10 seconds. That means real-time streaming performance. So the best practices here are really tune the batch size, so how much records you want to send at a time from a stream of data to the Lambda function. And this usually goes from 100 to 10,000 records. 10,000, I think, is the limit now. Tune the memory. Again, the memory gives you more CPU. So if you see that your Kinesis function is not able to keep up with the data processing, maybe if you give more memory and you have more CPU, it will be able to process more information. And if you use a specific device, look at our producer library that can help you create more compact records and be more efficient in data processing from the start. Last pattern before the final one with GraphQL. IT, we've seen lots of customers using Lambda functions to optimize what they do in their IT, to respond to alarms, to manage auditing. So everything that we need to do to manage our IT organization. So this is the Ops Automator. It's an example application that you can download. We build it, and it's available on our website. Basically, the idea here is that you can use CloudWatch events to fire a Lambda function periodically, every hour, every day, every 5 minutes. This Lambda function is getting tasks to do from a DynamoDB table. And currently, it supports doing the snapshot of EC2 instances or doing database snapshot of Redshift clusters. And if you want to use EC2 instance, you just need to add a tag to the EC2 instance, create where the operation is create snapshot. And what happens is this Lambda function will look what to do. It will trigger a task executors Lambda function that will look for the EC2 instances where they need to take the snapshot of the storage. And it will write everything that it does in logs so that you can understand if your backup is working or not. This is an example for image recognition, and we will come back to this in the last session. So if you want to process images, we have an artificial intelligence service that can look into an image and understand what's inside an image. And you can coordinate the workflow using step functions. We will see those in the last session. But step function can help you define a workflow that takes the input image and will extract the image metadata, will process the image with Amazon Recognition, create the thumbnail, and then store the metadata in DynamoDB. All of this is managed through a workflow that you can literally design, and it can help you map complex workflows that if you put everything inside a Lambda function, it could be more complex to build, or it can be difficult to audit and understand if everything is working correctly, or if you're losing some data. This is another example. There's Capital One. They built an open source project on top of this architecture. And the idea is that you can use CloudWatch events as your trigger for Lambda function. And CloudWatch events can tell you everything that is happening on AWS. So for example, if someone is creating a security group that gives internet access to one of your instances, you can check this event, trigger a Lambda function that can automatically remediate the error, so close the port, and send an SNS email notification to the administrator that received the notification. And a final example on this, Autodesk, they built an open source tool that they call Tailor, because they want to create accounts for the developers so that every developer can have their own account within their bigger account with everything set up with all the corporate standards that they have for auditing, configuration, networking. And they created this tool that can automatically provision all the resources using serverless functions for setting up an account in less than 10 minutes. It's much faster than what they were used before. So best practices for IT automation functions. So if you start to use APIs like EC2 APIs that are not meant to be used by consumers, you can incur throttling. So we don't expect you to do a EC2 describe instance more than 1,000. So 1,000 times per second is something that we control more fine-grainedly than what we do with S3. So check that, and our SDK will automatically retry if you get throttled. Use custom metrics to understand what you're doing. So post to CloudWatch the information, for example, on the snapshot you do, so that you have a baseline to understand what is working and or not. Use X-ray. We already saw an example in the previous presentation. And probably you need to disable function if something goes wrong, because this is IT automation. It's not something that maybe is double-checked like a traditional application that go in production. The best trick is just to give 0 to the concurrency of a function, and this will block any execution while you expect what's happening. Otherwise, you can disable the trigger and see why you have a problem. Final, and then we finish this quite packed hour. GraphQL. So we're switching a little bit more on the development side here. So normally, when we built APIs for the last 10, if not more years, the REST model was the standard. REST has lots of advantages, but it's also very granular, and it's difficult to express complex queries with REST. That's why a few years ago, Facebook designed this GraphQL model internally, then it made it available publicly. Now we've seen not just the Facebook SDK, but also GitHub, I think. They moved to GraphQL as a way to expose their API. And to make it available as a serverless service, we created this new service that is currently in preview. So you need to be accepted in the preview if you want to test it. It's called AppSync. And it can help you create real-time backends that can work also offline. So the flow with GraphQL is that you can create a schema. So with REST, there is no concept of schema, but here you can really define how you want to manage your data. Then you can connect data sources, and data sources can be DynamoDB tables, Lambda functions, or Elasticsearch databases. And in this way, you can map the schema to how the data should be written and read or written on these different data sources. And the platform will manage that. GraphQL manage also subscriptions, and subscription means that you can, from your application, say every time someone is changing this data from any client, any mobile app, any web application, send me a notification in real time so that I know that someone changed this data. We use transparently WebSockets in the browser or in a mobile app to manage all this complexity for you so that you can receive the notification in real time. And normally, you would just subscribe a function that is triggered every time it's changing something. So just to give you a very, very quick view on how this works, this is the AppSync console. And I have a demo application. It's the default demo. So if you want, you can, when you are accepted, you can test it. So this is the how a schema works for GraphQL. So you have an entry point where you define queries, mutations, and subscriptions. Queries is the way you want to read your data. Mutation, how you want to update or insert new data. And subscription is what you want to get notified in real time if someone is changing the data. In this case, I'm using 2 DynamoDB tables. So if I go on the data sources, I see that I have a comment table and an event table. So I can create events and then create comments on top of these events. If we go back here, you see that I can define an event type. So compared to the REST model, I can really define a structure for my data. The exclamation mark means that this is a mandatory field. All the other fields are not mandatory. So I have an event with a name, a location, a date, a description. And this can be linked to a paginated list of comments. And the comments, if we look for them here, they can link to an event, they have an ID, and they can have a content and a creation date. So I'm not entering into the tail of the protocols, but this is the way you can define your data model. And then you can define subscriptions that tells, in this case, we have a subscription to the comments. So every time there is a new comment on an event, I want to receive a notification. You use this annotation syntax to say that I want to be annotated by that. So if you do that, then we have an SDK that you can use. And this is, for example, a React application that we have on GitHub that totally works, that if you're in the right directory. So this is now already starting. So let's open another browser here. So we now have a couple of browsers. And this is the event, the web interface that is creating events, and then you can comment on an event. So if I create an event here, so this is a Builders Day in London. Nice event. I hope so. And you remember, events, they didn't have a real-time subscription, so I need to reload, in this case, to see the event. But then I can click here on comments. And since there is a subscription, if I add a comment, so it was not so nice, actually. And this is sent on the other side. And then I say, why? And then you can explain why. And you saw how everything was built. So there was, in the code, if you see the code of the application, there's no time. Everything is managed transparently. You just need to say, I want to use this subscription. And if anything comes, trigger this function, and then you can use this function to add comments or process the information. So it's super easy. And the other side is also that this framework is designed to work offline. So it's difficult to test, but if I disable the network, both these browsers can you can still create events and comments. And then when you go back online, they will synchronize the data. And there's conflict management in case of conflicts that you can do automatically or on the client side, depending on the business logic. So it's very good to build web and mobile backends. And it's a key trend that I would suggest you to have a look at, because I think more and more applications will use GraphQL to build their backend in the future. There's a summary, but we already went through all of that. There's lots of patterns that we have. I tried to share a few. Maybe it was somewhere interesting. I saw there where people were a little bit more on the bored side. But the nice story is that everything you want to build, we have architectural patterns that we can share so that you can really go into something that you need to invent and be the first to build these applications. Thank you. We take we take a 3 minutes break, because these two sessions are supposed to be one after the other, but I think we deserve 3 minutes, and then we start.